The next topic is the scalar product of two vectors A and B. So let's see the definition. So we have these abstract vectors A and B and say they have these geometric representations OA and OB. Well, we can always have this type of geometric representations where they start from the same point. Even if you find two representations which are like this, say this directed line segment represents A and this one represents B, then you can translate them parallel to themselves so that you can make their initial points coincide. Okay, so you can always have geometric representations like this. Alright, where O is the origin. Then the scalar product A dot B, we read it as A dot B of the vectors A and B is given by this equation. A dot B equals the magnitude of A times the magnitude of B times the cosine of theta, where what is theta? Theta is the angle between OA and OB, those two line segments which geometrically represent A and B respectively. So you can draw a diagram like this where OA represents A and OB represents B, and theta is the angle between them. But here itself you encounter a confusion. Which angle? Should you take this angle or this larger angle? The definition doesn't say anything. It just says theta is the angle between OA and OB. Strictly speaking, we actually have two angles, not just one angle. So which one should we take? And the answer is you can take any one of them. That is because if someone say considers this one and calls it theta and gets this value of the scalar product, someone else considers the other angle, which in terms of theta is 2 pi minus theta. We are of course measuring angles in radian. However, from elementary trigonometry, you know that cosine of 2 pi minus theta is the same as cosine of theta. So that way, no matter which angle you choose, you ultimately get the same value. However, there is another problem. And this is the problem you face. It's a special case where say one of the vectors is 0, A is 0. Then the line segment OA collapses and it becomes a single point. That's the legitimate geometric representation for the 0 vector, okay, as a point which has magnitude 0 and no direction. But then the problem is that theta loses meaning. Theta as an angle between OA and OB no longer makes sense in this case because there is no angle between a line and a point. So the definition actually does not cover this case. If one of the vectors is 0 or say both are 0, we need to define it separately. That means we need an extension of this definition. It's just a slight thing, but it needs to be done. And that small thing is this. If at least one of the vectors is the 0 vector, either A or B, or at least we are saying that means both of them can also be 0. In those cases, we define this scalar product to be 0 itself. What type of 0? 0 scalar. And we now see this fact also about the original definition and this slight extension also, that the scalar product of two vectors is a scalar, it's not a vector. You see the magnitude here, it's a real number, this one is also a real number and this one is also a real number. So in general, if both are non-zero, so that you apply this definition or at least one of them is 0, the result is a scalar. Next we have these laws of algebra for the scalar product, these three identities. A dot B, that is the scalar product of A and B in that order, equals the scalar product of B and A, B dot A. The order does not matter. And this follows immediately from the definition. I mean, there is nothing more to it. You then also have this distributive law. This one can be called commutativity, of course. You can describe it by saying that the scalar product is commutative. Just like ordinary multiplication of real numbers is commutative, 2 times 3 is the same as 3 times 2, both equal 6. Just like that we have this. Then we have this distributive law as well. A dot B plus C equals A dot B plus A dot C. And then you also have this kind of associative law where multiplication of a vector by a scalar, that is scalar multiplication, is there and dot product is also there. Lambda A, so here you treat this as one vector and B as the other vector. Their dot product equals lambda times A dot B. The author does not provide any proofs for these identities. Actually, they are just things which most of us already know. But still, if you want to see proofs of this, you can look in any vector algebra book, which is more elementary. I mean, this is not a book on vectors per se. This is a book on mechanics. So here we are just going to use these things, so we won't spend much time on these things. Besides these laws, next we also have some properties of the scalar product. If you take the scalar product of a vector with itself, then that equals the square of its magnitude, which you can see by just applying the definition. If A is a non-zero vector, then by the definition this scalar product is the magnitude of A times the magnitude of A times cos 0, because the angle between a vector and itself is 0. Does not matter if you take the other angle, it will then be 2 pi. Both cos 0 and cos 2 pi are equal to 1, so that way you get this. And if A is 0, well then by the definition means the extension of the definition, the scalar product is 0, and because A is 0, its magnitude is also 0, whose square is also 0, so in that case also you have this identity. And in this second one, the scalar product of two vectors is 0 if and only if they are perpendicular, and of course you understand that in this case both are non-zero, otherwise them being perpendicular does not make sense, or at least one of them is 0. Just like this one, the proof of this one also follows immediately from the definition. So let's see this next one instead. If I, j and k form an orthonormal basis, that means these are mutually orthogonal vectors, that they are perpendicular to one another if you choose any two of them which are distinct, and they are unit vectors, which is indicated by this hat, okay, not the normal arrow. So if you have such a basis, an orthonormal basis, then you choose any one of them and take the dot product. Well, we also call the scalar product the dot product, which is actually the more common name. The dot product of any one of them with itself is 1, which actually follows just from this one, because these are unit vectors. You take any one of them, the magnitude is 1, so that way you get 1. And if you choose distinct vectors, then the dot product becomes 0, and that follows from this one, because they are perpendicular, mutually orthogonal. That's why we have this. And then there is one more. This fourth one is also well known and something we use all the time. Say you have two vectors a1 and a2, each one of them has been expressed as a combination, a linear combination of basis vectors, where the basis is an orthonormal basis. In this way, lambda 1 I hat plus mu1 j hat plus mu1 k hat, that is a1, and a2 is lambda 2 I hat plus mu2 j hat plus mu2 k hat, where you understand that all these lambda, mu and nu, these are real numbers. Maybe negative, but they are real numbers. Then the dot product, the scalar product of a1 and a2 is lambda 1 lambda 2 plus mu 1 mu 2 plus mu 1 mu 2. You may already know how this one comes, but actually how this comes is using the properties that we saw today and the other things about the scalar product. First you write these two expressions, there will be a dot between them, and then you apply all the distributive laws, everything. So that way you get this. You try to actually prove this, okay, yourself without looking at anything, only using whatever we saw today, and see if you can get it. If not, you write in the comment section below, then I will tell you how to do it. Let's next see one example on this. Example 1.5. So here we have two vectors. Vector A is 2i hat minus j hat plus 2k hat, and vector B is 4i hat minus 3k hat. Then we have to find the magnitudes of A and B and the angle between them. Do you see one thing, that here also the author is saying the angle between them, but as we saw in the definition, there are actually two angles. By convention, we consider that angle which lies in the closed interval 0, pi. That means we are measuring in radians. If one wants, one can consider the other angle also, but that's the convention. So in that sense, it's okay to write like this, the angle. It's that angle between those two which lies in that interval. So we start the solution like this. We use that parts property and use this equation, which is that parts property. So that way we get the square of the magnitude of A as the scalar product of A with itself. And then we use the fourth one that we saw just now. So that way this product will be 2 times 2. You remember that lambda 1 lambda 2, that thing. 2 times 2, that is 2 square plus minus 1 square plus 2 square, which equals 9. So the magnitude will be 3. Its square is 9, so it can be positive only, so that's why it's 3. Similarly, we calculate the magnitude of B using the similar formula for B. So 4 square plus 0 square, I just simply wrote 0 square to show that we are using that fourth property, plus minus 3 whole square. So 16 plus 9, 25. So B has magnitude 5. Besides these magnitudes, we also need the angle between A and B. So let theta, and here we write explicitly, let theta which lies in this interval be the angle between A and B. Then we use this definition of A dot B. We already know that A and B are both non-zero. So we use the original definition, not that extension. So here we can directly use the magnitudes 3 and 5. So that way we get that A dot B is 15 cos theta. But we can of course also calculate A dot B separately using again that fourth property. So you go back and see what the vectors A and B are. It will be 2 times 4 plus minus 1 times 0 plus 2 times minus 3. That is, we are multiplying the corresponding coefficients of those I hat, j hat and k hat and adding them up. So that way we get 2. So the left hand side is 2 and the right hand side is 15 cos theta. And that means theta is cosine inverse of 2 divided by 15. And I need to say something about this cosine inverse here. And that is this fact. We use the principal branch of the cosine inverse function. You already know from trigonometry that the ordinary cosine function is not a one-to-one function of the set of real numbers onto this closed interval minus 1, 1. It is onto but not one-to-one, and as such its traditional inverse does not exist. If we want to make it exist, then we have to focus our attention on a restricted part of the set of real numbers, which you can do by considering different intervals. If you choose this interval, I am talking about the cosine function, okay, not the inverse function. If you consider the cosine function, that is if you restrict it to this interval, then also it becomes a function from this into this, onto actually, but then it becomes one to one as well. And so then it becomes a bijective function, so its inverse exists. That inverse is one of the possible inverses of cosine, and this is the principal branch of the entire cosine inverse function. That's what we are using here, and that's what we normally mean when we write cosine inverse. And that is why that angle between those two vectors is chosen in this interval, which makes it the smaller of those two possible angles. Next we have example 1.6, which is a result from geometry that we are going to prove using vector algebra. It has a name also, it's called Apollonius's theorem. But attributing names to mathematical discoveries, it's really complicated. Many names have been attributed to mathematicians just like that. I think you understand what I am trying to say. Many names have been misattributed. But anyway, let's see the statement. In the triangle OAB, M is the midpoint of the side AB. Then we have to show this. OA squared plus OB squared equals 2 times OM squared plus 2 times AM squared. So let's draw the figure, otherwise we won't really understand what it is that we are trying to prove. So this is the figure. So this is our triangle OAB, and M is the midpoint of AB, and we join O and M also by a straight line segment. OA squared plus OB squared. OA squared plus OB squared should be equal to 2 times OM squared plus 2 times AM squared. Now what we do, we consider vectors, position vectors of the vertices A and B relative to O as the origin. That means this vector OA and this one OB. Let's call this one A and this one B. And there are sentences here, you understand what those sentences are. Let A be the position vector of the vertex A relative to the vertex O, those things. Okay, so we are going to see the main thing instead of writing sentences. So A is OA and B is OB. Then from the section formula, because M is the midpoint of A and B, the position vector of M relative to O, that is this vector OM, will be 1/2 of A plus B, that we already know. Next we consider 4 times OM squared. OM squared is one of those terms that are there in that identity that we want to prove. So we consider 4 times OM squared. It will be clear why we chose 4 here. So what is OM? OM is the length of this line segment, which is the magnitude of the vector OM. So that means magnitude of OM square. That means magnitude of this square. Okay. There are some intermediate steps here that I did not write. The author also did not write. So you just think of the magnitude of this, which is itself a scalar multiple of a vector. The vector is A plus B and the scalar is 1 divided by 2. And now you go back and see the definition of scalar multiple of vectors. There you will see that you can take the scalar part outside of the magnitude. It will come not just as itself, but with an absolute value. However, because this is a positive real number, this itself comes out of magnitude, but still there is a square over it. So it becomes 1 divided by 4, which when you cancel with this 4, things vanish, and you are left only with the square of the magnitude of A plus B. Do not forget that besides A plus B, here there are two things. magnitude, and outside that we also have square. And now you go back to the first property of scalar products. This is a plus b dot a plus b. And then you use the distributive laws. Distributive laws I say because there are two. You can, well, actually you have to consider both the distributive laws. One of them tells you that a dot b plus c is a dot b plus a dot c, the one that we saw today. And the other one tells you that b plus c dot a, if you have a on this side, then also that goes inside the sum. B plus c dot a equals b dot a plus c dot a. So using both those laws, you can have this from here. And then what did we do? We again applied that same thing here and here. This equals the square of the magnitude of a, this equals the square of the magnitude of b. And if you use the commutative law, a dot b and b dot a are the same, so you get 2 times a dot b. And next we consider 4 times am square, which like this one is 4 times the square of the magnitude of the vector am. This time, however, instead of keeping the 4 outside like this, we push it inside. First it goes inside the square, it becomes 2, and then it goes inside the magnitude of am. Because 2 is positive, it just simply slips in and gets multiplied with am. So now you have 2 times am. Because m is the midpoint of AB, this vector 2 times am is the vector AB. And now if you use the definition of vector addition, a plus ab equals b. So ab would be b minus a. And then I did not write the steps that would come here, which are similar to this. You write this one as b minus a, scalar product b minus a, and then go through similar steps and then do whatever you need to do. Ultimately you will get this magnitude of a square plus magnitude of b squared, which is just like this one, but this time minus 2 times a dot b. And then we add these two equations. The previous one is, it's starting, I mean that side is not present. 4 times om squared, that equals this, and the other one is this. 4 times am squared equals this. So that way we get this plus 4 times am squared equals, you get twice of these two things, and these two cancel out. So 2 times magnitude of a square plus 2 times magnitude of b squared, and then you cancel 2 from both sides. So that way you get 2 times om squared plus 2 times am squared equals this square plus this square, which is just oa square plus ob square. Now you go back and see the example statement. This is what you had to prove.